Namaskaram. Welcome to Module 2. In this session, we will discuss Green's theorem and its applications. These are the solutions of previous homework. Before moving to the Green's theorem, first we have to define some terminologies. The first one is simply connected, and what is simple curve, and what about closed curve. We know what is a smooth curve. Smooth curve means differentiable curve. Okay. First we have to define the simply connected region. A simply connected region means a region without no holes. You say simply, okay, suppose you consider this region, the solid region. In this region there is no holes. So this region is an example of a simply connected region. Okay, connected without holes. Suppose you think about another region like this. Okay, and our region is this one. Okay, so the region without this portion, like a hole. Okay, this region is connected, but it is not simply connected. This is simply connected region. That's the idea of simply connected. A region without holes. That's all. And simple curve. Simple curve means a non-intersecting curve except endpoints. Okay, for example, this curve is not simple because it is intersecting at this point. Okay, but this curve is simple. It's a non-intersecting curve. Okay, and this is not closed, but this is closed. Okay, so this is not simple, neither simple nor closed. This is not closed but simple. This is simple closed, non-intersecting and closed curve. That's the meaning of simple closed curve. Okay, so these are the technical terms in this definition. Let R be a simply connected plane region and whose boundary is a simple closed smooth curve. Okay, suppose this is our region, then this is our boundary of this region, and this region should be simple. Okay, it is clear that in this region it is simple, closed, and it is differentiable. Oriented counterclockwise direction. Oriented in this direction, counterclockwise direction. If fxy and gxy are continuous and have continuous first order partial derivatives on some open set containing R, a set inside R, maybe full R, then the Green's theorem states that integral over C fxy dx plus gxy dy. We know what is this in terms of vector notation also. There is an integral over C f dot dr, where dr is dxi plus dyj, and f is fxyi plus gxyj. Okay, anyway, we know how to evaluate this integral in basic rules. And Green's theorem states that we can evaluate this integral using a double integral. Double integral over the region R. We know how to evaluate double integral. Okay, and we have to we can convert a single integral as a double integral, and conversely a double integral as a single integral using Green's theorem. That is, Green's theorem helps to convert a double integral over a plane region. Now here R is a plane region. Plane region in terms of a line integral around its boundary, and vice versa. Okay. Okay, first problem. Use Green's theorem to evaluate this single integral along a curve. The C is nothing, it is a triangular region like this. Okay, so we have to evaluate the single integral using Green's theorem, that is using double integral. We know how to evaluate the single integral using our elementary methods. Okay, so what is our Green's theorem? Okay, so our Green's theorem states that integral over C f dx plus g dy is equal to double integral over R, and R is a region enclosed by C. Okay, R is a plane region, dou g by dou x minus dou f by dou y dA. So we have to compute this double integral. So here C is nothing, this simple closed curve is C. So R is the region enclosed by this curve, that is inside this triangle, that is our R. Okay, so we have to integrate this integrand over this R using a double integral. Okay, So what is f? So here f is equal to x square y and g is equal to x. So we can easily evaluate dou g by dou x and dou f by dou y and plug all these values in this equation. Okay, then we get double integral over r 1 minus x square dA. Derivative of g with respect to x is 1. This value is x square dA. Then how to compute this double integral? That is very easy. Either first we consider a vertical strip, then we move the vertical strip such a way that to cover this entire region. Otherwise you can consider the horizontal strip, then move the horizontal strip such a way that it covers this entire region. Okay, anyway I want to take the vertical strip. Consider the vertical strip first of all. So what is the range of y? So here y value is always 0, and what is the y value at this point? Okay, to find the y value, first of all we have to find the equation of the straight line. The equation of a straight line passing through 0, 0 and 1, 2. This equation of straight line is very simple, that is nothing, y is equal to 2x. Okay, so y value is always starting from 0 ending at 2x. So we can set this limit as like this, 0 to 2x, 1 minus x square. The order of integration is dy dx. First we have to integrate along y, so dy dx. And to cover this entire region R, this inside this triangular region, that is our R. Okay, to cover this entire region R, x should varying from 0 to this point. Okay, then only this strip cover entire triangle. So x is varying from 0 to 1. So 0 to 1. Okay, this is the setup of this integral. Now it is very easy to evaluate. First of all, we have to integrate with respect to y, then substitute the limits, then we have to integrate with respect to x. Okay. So 1 minus x square is a constant with respect to y. So integration become y 0 to 2x dx. When we substitute 2x, this become 2x minus 0, that is 2x. So by expanding the 2x into this bracket, this become integral 0 to 1 2x minus 2x cube. Okay, dx. And again you can integrate this with respect to x, then we get that is equal to ultimately 1 by 2. Okay. Yes, answer is 1 by 2. Second problem, use Green's theorem, find the work done by the force field fxy is equal to e raised to x minus y cube I plus cos y plus x cube j on a particle that transfers once around the unit circle x square plus y square equal to 1 in the counterclockwise direction. Okay, that means we have a force field in some directions, and we have a particle is moving along a unit circle in the anti-clockwise direction. Then we have to find the work done. We know that work done is equal to integral over c f dot dr, where dr is, in this case dr is dxi plus dyj and f is this one. By taking the dot product, this expression become integral over c e raised to x minus y cube dx plus g into dy. So in this case our f value is e raised to x minus y cube and g value is cos y plus x cube. We know we know that we can evaluate this single integral using a double integral. Okay, so here the c is enclosed by the region inside the circle. So our r is this region. This is our region r. So we have to integrate along this circular region. Okay, so by Green's theorem, this integral become double integral over r. R is the inside of the unit circle. Dou g by dou x minus dou f by dou y dA. So that is equal to double integral over r. And dou g by dou x, this is our g. So if you differentiate with respect to x, this time becomes 0. This is 3x square. Minus, what about dou f by dou y? This is our f with respect to y, then this time is 0. This is minus 3y square. Minus 3y square. So this minus minus become plus. Okay. So how to integrate this over this region R? Either you can evaluate this double integral in Cartesian form or polar form. Because this is a circular region, better we use the polar form. Okay. So in polar form, what about the integral? Double integral. This time is actually 3 times. The integrand become actually 3 times x square plus y square. Okay, in polar representation, we know that x equal to r cos theta and y is equal to r sin theta. So it is clear that x square plus y square equal to r square. So this term becomes 3r square. Okay, and what about dA in polar form? In polar form, dA become r dr d theta, r dr d theta. Okay, so this is our integral. Then what is the limit of r and theta? We have to cover this entire region, entire circular region. Okay, so what is the range of r? R should vary from this point to this point. Okay, so what is the range of r? R is varying from 0 to 1 because the radius of the circle is 1. So r is varying from 0 to 1. And to cover this entire circular region, theta should vary from 0 to 2 pi. So 0 to 2 pi. So we have to compute this integral. Okay, now this is very easy to evaluate. First you integrate with respect to r. This time is actually r cube. So first you integrate with respect to r, then with respect to theta. Okay, after integration we get, after the first integration, that is with respect to r, this becomes 3 by 4 0 to 2 pi d theta. Then after the second integration, this term becomes 3 pi by 2. So this is the work done due to this force around this unit circle. Okay, yeah, 3 pi by 2. Okay, this is the another application of Green's theorem. We can evaluate area of a plane region using Green's theorem. We know that the area of a region is given by this formula, double integral over r dA. Okay, this is the formula of area. Then how to convert this double integral as a single integral? That is our main problem. So we know that double integral over r, this portion into dA is equal to a single integral like this. Okay, so we have to find area. This double integral is area only when this integrand is 1, isn't it? If this integrand is 1, then this double integral gives area. For what values of f and g this integrand is 1? That is our question. For what values of f and g this integrand is 1? Yes, if you choose g equal to x and f equal to 0, suppose we choose g equal to x and f equal to 0, then what about first part? This portion is 1 and this portion is 0. So right hand side gives area, isn't it? And in that case, what about the left hand side? Our g equal to x, so we can replace this by x and f equal to 0. So this portion is 0. So this is integral x dy. Okay, that's why we get the first formula. So integral over c x dy gives the area. C is nothing, C is the simple closed curve enclosing the region R. Okay, we have to find the area of this region R. Similarly, we can find one more formula, because then if you choose g equal to x and f equal to 0, automatically this is 1. Similarly, if you choose g equal to 0 and f equal to minus y, then again this integrand is 1. If g equal to 0, this term is 0, and f equal to minus y, the derivative is minus 1, then minus plus 1. Okay, so this choice also gives the area. Corresponding this choice of g and f, what about the left hand side? Here f is minus y and g equal to 0. So this is integral minus dx. That's why area equal to integral over c minus y dx. Okay, so these two formulas gives the area. Clear? Then by comparing these two formulas, we will get one more formula. This formula is also useful because area equal to this one and area equal to this one, the sum of these two formulas, what happened? 2 times area equal to integral over c x dy plus integral over c minus y dx. Okay, we have to find area. So what is area? Area equal to 1 by 2 times integral over c minus y dx plus x dy. Okay, so for evaluating area, we have 3 formulas using Green's theorem. Okay, next problem. Use a line integral to find area enclosed by the ellipse x square by a square plus y square by b square equal to 1. Okay, so suppose this is a equation of ellipse and this length is a and this length is b. So we have to find the area of this ellipse. So first of all, we have to identify the curve C. C is nothing, it is the boundary of the region R. Okay. So by we can evaluate the area using Green's theorem, any of the three formulas. So here we use the last formula, that is area equal to 1 by 2 integral over C minus y dx plus x dy. Comparatively, this is easy. Okay, that's why we use this formula. You can use any formula, no problem. First two formula also gives the same answer. Okay, I am going to use this third formula. So this is equal to 1 by 2. Okay, we know that to compute this line integral, we have to find the parametric form of this curve. See, what is the parametric form of the curve ellipse? That is x equal to a cos t and y is equal to b sin t. So this is the parametric form of this ellipse, and t is varying from 0 less than or equal to t less than or equal to 2 pi. So this is the range of for the parameter t. Okay, so how to evaluate this line integral? This is integral 0 to 2 pi what over minus y, that is minus of b sin t into, instead of dx, we have to substitute derivative of x dash of t dt. Okay, what is x dash of t? Here actually x dash of t dt. And what is x dash of t? That is minus a sin t, isn't it? So this is minus a sin t dt. And what about the second term? What is our x value? That is a cos t into, instead of dy we use y dash of t dt. That is a formula for evaluating the line integral. Okay, so what about y dash of t? That is b cos t. So this is b cos t dt. Okay, so this integral become 1 by 2 by taking sum of these two terms. We get 0 to 2 pi ab times sin square t plus cos square t, and this is 1. So this become 1 by 2 integral 0 to 2 pi ab dt. So upon integration we get this is 1 by 2 ab, this is t, and 2 pi to 0. When we substitute in the upper limit, this is 2 pi. Okay, so into 2 pi. So this is equal to pi ab. So pi ab is the area of this ellipse. Okay. This is your homework. Thank you.